Hello everyone, I am Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course Operating Systems. We are learning different CPU scheduling algorithms. As part of that, in today's lecture, let us understand about what is this round robin CPU scheduling algorithm. Up to our last lecture, we learned about different types of CPU scheduling algorithm. I'll just quickly revise them. We understood like CPU scheduling algorithms are of two types, preemptive and non-preemptive. Non-preemptive algorithm is nothing but once a process is given a chance to be executed by the CPU, then until and unless it finishes its execution, it will not be releasing the CPU. Whereas coming to preemptive, depending upon the algorithm, the CPU may switch between the processes. So as part of non-preemptive scheduling algorithms, we have learned three types of CPU scheduling algorithms, FCFS, SJF and priority. I hope you all are clear with those CPU scheduling algorithms. From today's lecture onwards, we will be learning about preemptive scheduling algorithms. First one is round robin CPU scheduling algorithm. So let us see what actually this round robin CPU scheduling algorithm is. So, as I already told you, this round robin CPU scheduling algorithm is preemptive CPU scheduling algorithm. That means the CPU, once given a chance to the process, even though it has not completed the execution of that process, the CPU may switch to the other process. How it is going to happen and all we are going to understand. Now, in this round robin CPU scheduling algorithm, the CPU may shift to the next process depending upon the parameter called time quantum. What is this time quantum is? A certain time period will be given. If the time period is over, then forcibly the CPU will be given to another process which is waiting in the ready queue. Okay, so that means the process that is preempted. So whichever process we are executing now, if the time period is over, that has to be forcibly removed and it has to be added to the end of the queue. Right? So this is how round robin CPU scheduling algorithm will work. So let us understand this one with some example first. So in this example, what I'm considering is I'm considering three processes P1, P2, P3 and the three burst times are given. Here I have not considered any arrival time. Understand here. That means all the processes P1, P2, P3 has arrived at the same time and all has been added to the ready queue. Let us consider this is our ready queue, right? And here I am considering the time quantum is 2. That means the CPU can execute a particular process for 2 seconds only. In the question, P1 requires 4 seconds, P2 requires 3 seconds, and P3 requires 5 seconds. Right? So let us understand how the CPU will be switching between the process. Now, as all the three processes are there in the ready queue like this, then CPU may take any process. So let us consider P1 has got the chance. So P1 requires 4 seconds, you can see here. But even though it requires 4 seconds, it will be executed for 2 seconds only. Did you see here? It will be executed for 2 seconds. Why? Because our time quantum is of 2 seconds only. Right? Now, after executing for 2 seconds, it has to be forcibly removed and it has to be added to the ready queue and then the next process has to be taken. So next process in our queue is P2 that will be given a chance and it will be executed for 2 seconds. Even though it requires 3 seconds, it will be executed for 2 seconds only. And then the process that is available in the ready queue is P3 that will be given a chance which will be executed again for 2 seconds. You can observe here P2 remaining again 2 more seconds it requires, P1 requires 2 seconds, P2 requires 1 second and this requires 3 more seconds to be executed and all these have done their turn and already again we have P1, P2 and P3 in our queue and P2 will be given a chance again. So P1 will be executed for 2 more seconds. So now this 2 seconds is done. We can remove that. And P1 requires only 1 second. That also has been executed here. And then P3 requires 3 seconds, out of which 2 seconds will be executed. And again, it will be added to the ready queue. Understand here, these two will be removed. P3 got a chance here. And this has been executed for 2 seconds. And no other process is there. Again, P3 will be added. So that only will be given a chance, which will be executed for 1 more second. Right? So this is how CPU, if you can see here, the CPU has been switching between one process to other process once the time quantum has been expired. So that's why it is called as preemptive scheduling algorithm. Preemptive scheduling algorithm is nothing but CPU will switch between the process even though the first process has not been completed its execution. Right? Let us take one more example where different time arrival times are there. Here in this example, there is no arrival time. That means all has been arrived at the same time. Now I'll take one more example where we have considered different arrival times. Right? This is the final output of the first problem, how it has been executed. Right? Now let us consider different arrival times. You can see here different arrival times. P1 has arrived at 0 second. P2 has arrived at 1 second and P3 has arrived at 2 seconds, right? And the time quantum here I am considering is 3 seconds. Now how it is going to execute, let us see. First P1 will get a chance. Why? Because in our ready queue, I will draw the ready queue here. At arrival time 0, P1 is only arriving. Okay, so P1 is the only process that will be getting the chance. Now P1 will be added to the queue, to the Gantt chart here. Now for 1 second, if it is executed at 1 second, did you see we got P2. So P2 will be added to the ready queue and 2 seconds it will be executed, and at the second you can see P3 is also there. P3 will be added to the ready queue. Right? But we have to execute this process, P1 process for 3 seconds, but it requires 4 seconds. You can see here it requires 4 seconds, but it will be executed for 3 seconds only because of the time quantum. Okay, so we have been executed for 3 seconds. Now what we will do, P1 will stop its execution forcefully, then it will be added to the ready queue here. So we will have the in the ready queue P1 because it has not completed its execution, and you remember here it requires 1 more second to execute. Right? Now which process has to be added? Because P2 came into the ready queue first, this will be given a chance and then P2 will be executed. You can see here P2 requires 5 seconds, but even though it requires 5 seconds, will be executing for 3 seconds. Always remember, for each second you are executing, you need to check any new process is arriving. In our program, in our example here, 3 processes are there. Already they have been added to the ready queue here. So no problem. But if you have more process, then for each second you need to check any new process is arriving at that particular second. Then you need to add that one to your ready queue. Right? Now this will be executed for 3 seconds. Right? So we are in the 6th second. After executing for 3 seconds, it has to be forcibly removed. So it has been executed for 3 seconds. It requires 2 more seconds. You can see here in our ready queue, P2 will be added. Right? Now the chance is given to P3. So P3 will start its execution, which requires 4 seconds, but because of the time quantum, it will be executed for 3 seconds. So 6 to 3 seconds is 9 seconds, and then it will be forcibly removed. What I'll do, I'll add the queue here, continue the queue here. P3 will be added here. Right? So it has been done. Now which process will be there? Is there our P1 process is there, which requires only 1 second. That's why from 9 to 10 it has been executed, which requires only 1 second. So that is also done. Now as it has completed its execution, no need to add that one to the ready queue again. Alright. Now the other process we have is P2. P2 will start its execution, which requires 2 seconds. Our time quantum is 3, so it can finish its work in 2 seconds. So 10 to 12 is 2 seconds. It has completed its execution. Right? And the only process that is left is P3. So P3 will be given a chance to execute for 1 second. That is the required time. So 12 to 30, it will be executing the things. So this is how with arrival time, if you have a separate arrival time, at each second, if any process is arriving, we need to keep a track of that one, and then we need to add that one into our ready. That is how round robin will work. Let us take one problem. We'll follow this approach and we'll see how to calculate the waiting time and the turnaround time. Right? So I'll take one example here. You can see here, I have considered 5 processes. Each process, what is the first time required and what is the arrival time required has been mentioned in the program, and the time quantum is given as 2 seconds. Okay. So let us draw the Gantt chart, and here I am maintaining the timer also for our understanding. Why I am maintaining timer here? Because at each second we need to check the arrival time. Any new process is coming, that has to be added to the ready queue. So let us consider this is our ready queue. Okay. So always we need to have a habit of having the ready queue, timer, and then we need to draw the Gantt chart parallelly. Okay. So the first one is at time second 0 second. You can see here we got a process P4 that has to be added to the ready queue. Because that is the only process that is available in the ready queue, that will be taken from the ready queue and it will start its execution. How many seconds it requires? It requires 3 seconds, but because our time quantum is 2 seconds, it will be executed for 2 seconds only. But always remember, whenever you are executing, check the timer. Okay. And at the any process is arriving or not, you need to check. You can see P4 has been executed for 1 second, and at 1 second you can see we got a new process called P3 that has to be added to the ready queue, right? And P3, our time quantum is, you need to remember, time quantum we have given here is 2 seconds, I think. So 2 seconds it will be executed, and at that second you can see here we got P1 will be added to the ready queue, right? So as per our time quantum, 2 seconds our process P4 has been executed, and forcibly it has to be stopped its execution and it has to be added to the ready queue. P4, it has to be added to the ready queue, and any process in the ready, this will be taken next and it has to start its execution. So you can see P3 will finish its execution. Now P3 requires how many seconds? It requires 8 seconds. You can see here P requires 3 seconds, out of which we have executed 2 seconds. So remaining time is 1 second. Okay. Now P3 requires 8 seconds. Even though it requires 8 seconds, our time quantum is 2 seconds only. So it has to execute 2 seconds only. So P3, let us execute for 1 second. 3. At 3 seconds, any arrival time is there? No arrival time is there. It will execute for 1 more second. So at 4 seconds, we got P5. So P5 will be added to the ready queue. Right. So now P3 has completed its execution for 2 seconds. That is at 4th second. Now P3 will be forcibly removed from this, and that will be added to the ready queue. You can see here, and we have P1. Earlier I will show you. We have P1 here, and P3 has to be removed and kept here, and P1 will be given a chance. So that is what we are doing here. P1 will be given a chance. P1 requires how many seconds? 6 seconds. So let us execute for 1 second. At 5th second, any process is coming? Yes, we got a process here, P2, that has to be added to the ready queue. That is what done here. It has been added. Now, at 6th second, any process is there? No process is coming. Now, P1 has completed its 2 seconds. Even though it requires 6 seconds, we can give only for 2 seconds. So, 2 seconds are done. So, out of 6 seconds, it requires still 4 more seconds to be executed. Right? Now, that has to be added. P1 has to be added to the ready queue, and the process P4 has been waiting first here, that has to be given to the CPU. Now P4, which requires 1 second only, so that has been executed for 1 second. That's it, and P4 has completed its execution. No need to again add that one to the ready queue. Now the process that is waiting for this one is P5. P5, if you see, it requires 4 seconds. Observe here, whenever a process completed its execution, I am marking that one the red color. Okay. Now, P5 requires 4 seconds. That will be executed for 2 seconds. So, always remember we need to check the timer, but because all the process, our process has been added to the ready queue, I am not keeping a track of this arrival time. If that is not the case in the another example, you need to always keep a track of this arrival time if any new process is arriving. Okay. Now P5 has completed 2 seconds. So out of 4 seconds, it requires 2 more seconds to be executed. Now P5 should be added to the ready queue, and a process P3 is waiting. So that's why it has been added to the ready queue. And P3 requires 6 more seconds, but only 2 seconds we can execute. So 2 seconds we have executed. It has to be forcibly stopped here. It has to be added to the ready queue, and P2 will be getting a chance now. So P2 will be executed. Right? Now, if you follow in the similar fashion, next P1 will be given a chance. P1 requires 4 seconds, but only 2 seconds will be added. Right? And then P5 requires 2 seconds. So 2 seconds. P3 requires 2 seconds. You can see I am highlighting with the red color, means it is completing its execution. It has been completed its execution. And then finally P3. So it has completed its execution at 23 seconds. So this is our final Gantt chart that has been done for the given process with the given burst time and the given arrival time, and no process is there in the ready queue. So 23 seconds, in 23 seconds we have completed our execution. We have considered our time as 2 seconds. Right? Now with this information, let us calculate the waiting time. How to calculate the waiting time? You already know the formula for the waiting time. Waiting time is nothing but start time minus arrival time. Okay. Now you can see P4. Let us calculate for P4 first. What is the start time for P4? It is 0 seconds, right? This is 0 seconds, and then the arrival time for P4 is also 0 here, right? So let us see, P4 is 0 minus 0. So that is, and then you need to consider start time as arrival plus any other places it has been waiting or not, that also we need to add in the preemptive scheduling algorithm, because we are not completing our process execution in one slot. In multiple slots it gets the CPU time, and then at a particular time it will finish its execution. So whenever you are talking about preemptive scheduling algorithm, you need to calculate the waiting time, start time, arrival time, and the waiting time in the this one also. So P4 you can say 0 is the start time and the arrival time is 0. But at what particular time, if you see from this time to this time, whichever is highlighted with red, the P4 is waiting in the ready queue to get its chance again. So this time has to be added. What is that time? That time is 4 seconds. So 2 seconds here and 2 seconds here. Again, you check somewhere, anywhere P4 is there, nowhere P4 is there. So that is your total waiting time, which is 4 seconds, right? Next one. Let us consider about P3. Now P3, what you need to do? You need to consider the start time minus arrival time plus you need to consider any other waiting time in this. So I will tell you start time is 2 seconds. Okay. Arrival time is what we are talking about P3 1 second plus any waiting time you have. Waiting time is from here to here it is waiting, and from here to here it is waiting, and from here to here it is waiting, isn't it or not? So that is what we need to add here. So 2 minus 1 plus this highlighted with red and this highlighted with red and this highlighted with red, you can see from here to here 2 plus 1 plus 2 which is 5, and 2 plus 2 plus 2 which is 6 seconds, and this is 1 second. 19 minus 21 is which is nothing but 2 seconds. So total of 14 seconds it requires. It is having the waiting time. Similarly P1, P5, P2 also you can calculate, and you can finally you can see the average waiting time we are getting is 9.2. I hope you all are clear with this waiting time calculation. Now let us calculate the turnaround time. You already know turnaround time formula is completion time minus arrival time. So P4 completion time is, you can see here 7 seconds minus arrival time is 0 seconds. So 7 minus 0 is 7, right? And then for P3, it has completed at 23rd second and arrival time is 1, so 22. And P1, you can see P1, it has completed at 21 seconds. Last completed, don't consider the in-between completion time. That is not the final completion time. Okay. So 21 minus 2, which is 19. And then I think P5 you can see 17. P5 is 17 minus 4, and then P2, where is P to the last time? It is 13 seconds and then 5. So this is how turnaround time is calculated, and if you take the average of these values, you may get the value of 13.8. So the only thing here you need to observe here is how the CPU has been switching between the process depending upon the time quantum that has been considered. Right? So this is about a round robin CPU scheduling algorithm. The input you will be provided is number of process, what is the burst time, arrival time, and you will be provided with the time quantum only. Okay, and then you will be asked to calculate the waiting time and the turnaround time. Right. So this is how the algorithm works. But here there are some observation you need to consider. What is the observation is it will act as FCFS with preemption. Why it is called as FCFS with preemption? Because you can see from this diagram whichever comes first that will be given the chance. Right. That is what we are doing. In the ready queue, whichever will be coming first that will be added given the chance that many number of seconds of time quantum. So that's why it is told like it acts as FCFS with preemption. Now another observation is if the time quantum is very less, then the context switching is very huge. What do you mean by context switching is the CPU switching between the multiple processes. So if the time quantum is very less, if you take 1 second, then the CPU will switch between the process for each second. That is what the two observations you need to consider. So it is considered as an FCFS with preemption, and the context switching will be used if you take time quantum less. Right. So here is one assignment I'm like projecting here. Try to solve this problem with the given time quantum 3. Try to calculate the waiting time, average waiting time, and average turnaround time for this problem. I hope you all are clear with this today's lecture. In the next lecture, we'll learn another preemptive scheduling algorithm. Let us all meet in the next lecture. Until then, thank you all of you.